was out in the foothills yesterday. It was fantastic. The wind was crazy. The pines were going nuts. Like, couldn't even hear anything but the roar. It was like being by the ocean. It was superb. All right, friends, let's settle in for a few minutes and then get rolling on some new stuff. Kind of new stuff. Still calculus, which I have a funny story about in a minute. So just taking some time to do an inventory of where you are at right now. Just letting go of all obligations and plans. For the next minute, just giving yourself a treat. Just do nothing. Find yourself doing something. Just stop doing that. Come back to just noticing what's going on in your heart, in your body, but not your mind so much. You have trouble letting go of thoughts? Maybe try focusing on your right foot. Noticing whatever is to be noticed there. Just gently coming back to calc room, calc stuff. So, exam done, good job. I know that some people were disconcerted by the exam. I just want you to know you will have a chance to do corrections. So, usually I don't like to do grades early. I will definitely have them back on Monday, but I don't like to post the grades early, especially for this first round because people get freaked out. But the way corrections work for me is that you'll be able to earn back 50% of whatever was taken off on any problem where more than one point came off. Because the point is to learn. I don't care if I give everybody an A. I would love to give everybody an A. I'm not concerned about grade distributions. I'm a full professor. I don't have to worry about most shit anymore. As long as I don't attack anyone, I think I'm okay. And I don't plan on attacking anyone. So that's good news for all of us, probably. Is there any questions? Oh yeah, web work. New web work up, due next Wednesday, maybe start on that so that we can talk about it on Monday. That would be great. Things are going to become a little more concrete at this point, as concrete as anything can be. So if you're a person who's had calc before and you're like, what is this thing we're doing? Because it's not like the calc I had. You can't use the power rule. What's up with that? This is going to be like the calc you know. So we're going to have a bunch of rules that we need to learn and practice with. And we're going to be learning the calculus. And calculus just means method. And in particular, we're going to be learning differential calculus, which is all about derivatives. Bless you. Bless someone for something there. And then like this, so this is up till like the last 3 weeks of class. And then the last 3 weeks of class, we will do integral formulas. And that will hopefully, that'll give you a taste of what the other side of calc is all about, the opposite of differentiation essentially. And it'll get you, if you're going on to Calc 2 with me this fall, that sounds great. We got to get you ready for that so you have a little bit. And then when you come back, there'll be less to warm up on in August, the end of August. So, yeah, I'm sorry. So I asked for questions and then started babbling. Anybody have any concerns or questions or anything? No? Okay. Great, great, great. So, let's start talking about derivatives again, but in a whole different way, much higher level than where we've been at. The only time you might see a derivative definition, the limit, h goes to 0, all that stuff, is when we're cranking out a formula together, but you're done doing that by hand. You're done finding limits. We're just going to be doing derivatives for quite a while. So let's get there. Derivatives, again, I would say revisited, perhaps, would be a word. So, when I've got a function f of x, and I do this thing, the derivative, now I'm going to put the definition up again. That is this process, which you know. You've got that, you wrote that at least on your sheet, you've done it a dozen times or more. You've cranked that thing out. So when I write this notation over here, this means do this to the function, right? And let's think about then what that means. If I've got this function, I'm finding the slope of the tangent line. So if this is x, and this is f of x, the slope of this is f prime of x. That shouldn't be news at all. What we haven't done a lot of is continuing this process on. We did go to the second derivative. So if I say this, notice how I've got the d squared and the x squared in the bottom, pure notation, not a fraction to be divided or simplified. This is just notation. Meaning take the derivative of the first derivative. So keep applying those derivatives here. We also have some other notation we've used. This is just f prime of x. This is f double prime of x. But we could keep on going on with this theoretically. So we can also talk about third derivatives of f of x. And that's the derivative of the second derivative. And that's f triple prime of x. And then after that, the notation starts to get a little hairy. We don't keep putting those slash marks. So like for the fourth derivative, just showing you some notation right now. We usually actually go to this little, after 3, we put a little parentheses with the depth of the derivative in there. So this is the fourth derivative right here. Fourth derivative of f. Straight up notation that you're going to want to know, going to want to feel comfortable with. But it is just, you know, some definitions. Let's start talking about some now. We're going to get a bunch of formulas out today. So derivative formulas. That's really what today's all about. And eventually you're going to have a table with all sorts of things on it, some of which we've derived, some of which are just too big a pain in the ass to derive, and so you look at a table and you grab the formula. So let's just take a look at this. What is the derivative of a constant here, k? So k is a constant. What's the derivative of a constant? 0. Nice. And let's prove that to ourselves. So that's just 0. No matter what that number is, pi, e, 1,010, it just goes to 0 because a constant has this graph. So let's see here. So this is y, this is x, and this is just y equals a constant. And we see there the slope is 0. And the slope and the derivative are the same thing. So we could derive that just from looking at the graph and our knowledge of tangent lines and stuff. And then we've got some others, but let's get straight to, I'm not going to derive this one because it gets pretty fancy. So the following rule is how we do powers of x. And watch the rhythm here. This is all rhythms that you just have to get used to. Bring the exponent out front. Take x, decrement the exponent by 1. Now to prove this in general is pretty fancy, but we've already seen some examples of this. We did them by hand. So the derivative of x squared was 2x, and we suppressed the 1, but we didn't have to. So notice how the derivative of x squared, I brought the 2 in front and decreased the exponent. We may have done this one, I think we did, x cubed, when I was talking about the Pascal's triangle back in the day, like a million years ago, was this. Brought the 3 out in front, decreased the exponent by 1. So again, this is called the power rule. And it's your main workhorse. You're going to be using this thing every day, over and over, in various ways and forms. This is like the core formula to remember. So let's take a look at some examples. We've already got 2. Here's 2 on the board right away, but now we can get fancy and do all sorts of things. So examples. We want to find the derivative of x to the 100th power. I don't have to go to the formula, that would suck. I go to the power rule. I bring the 100 down in front and decrease the exponent by 1. So I've got a new exponent. Let's take a look here at something else. While we're at it, what is the second derivative of x to the 100th? Well, that means I just have to take derivatives twice. So this is the derivative of the first derivative. So I do that process once, but now I have to do it again. And that's what this notation tells me. You still have to do that, dude. So watch this. I'm going to bring that 100 along with for the ride. We'll take a look at some properties in a minute that'll make this solid. And then I take the derivative of x to the 99th. So a 99 comes out in front, and the exponent goes to 98. And then I could simplify that if I wanted. Let's just go ahead and do it. 9900x to the 98. It's going to get pretty crazy after that, so we'll stop. It's going to get a little large. Using the power rule, let's have some more fun. What about something like this? Oh man. Here's what I don't want to do. Here's what you might do at some point, because it just happens. You just take the bottom, you take the derivative of the bottom, and you're like, oh, the derivative of x, come over to the power rule, the derivative of x to the first would be 1x to the 0. So just 1, because x to the 0 is 1. That's not what we want to use here, because look at the pattern. It's just a variable to a power. That is a fraction with a variable to the power in the denominator. So I have to rewrite this. The first step is rewrite into this form, variable to a power. So that means it's the derivative of x to the negative first. And now I can apply the power rule. And I do so. I bring the negative 1 out in front, put a little paren there to keep us safe, and then decrease by 1. So check it out. That exponent went to a negative 2. And my final answer is this. And I can rewrite it like this if I want. And you should be comfortable with both of those forms. Stop for a second. Any questions or anything that's troubling at all? All right. Cool. So let's make it even fancier. Derivative of the square root of x. Okay, that's not x to a power, so I have to write it as a power. That's derivative of x to the 1/2, so that's how roots go, they're fractional exponents, and that's 1/2 x to the negative 1/2. Power rule. Exponent out front, decrease exponent by 1, and then I could get fancy with this if I wanted. Notice how that's 1, so this thing right here, if you're confused about what just happened, that's this. So you multiply that by 1/2, you get this. And you know, if you want to go back to that old notation, that's cool. So now it's your turn. Let me give you some problems. Practice. All right, my friends, what is, and just work on this on your own, and then we'll talk about it in a minute. So please find these derivatives. That is a cube root of x. Karma-free quiz right now. Only you and your math know what happened. Maybe me if I come look at it, but I won't judge. Also available for consultation. Free consultation if you need it. That is a cube root. Yes, sir. Yeah, same as that. Absolutely. Yeah, it's hard to see. This is a cube root of x in the bottom here. Make it a little clearer. Probably looks about the same one. Sorry, but I tried to improve. Well, how did we start on 1 over x?
So like this.
Yeah.
But it's maybe up and up a little bit here today, 3 or just.
Well, that's a 2 down there. Is it? No, is it cube?
Yeah.
Is it a cube? Okay, cool.
So I don't know if it'd be that.
Well, it's x to the negative third.
Okay.
Yeah. It's just
I
like,
wasn't
there
sure
you
if
go.
that exponent was transformed.
Yeah, there you go. So if you got 1 over something, it's just x. Just make the exponent negative.
Okay. Sounds good.
And now you're cruising. You're doing good, Carla. Yeah.
But it's negative x to the third.
It is that, wait, where's the negative?
Well, there's a negative here.
Well, that was after the derivative.
Okay.
So there's no negative in the original, so it's just x to the negative third.
So it would be maybe?
I don't think you're following the rule. First off, there is no negative in front. But even if you were, that wouldn't be the rule. Negative 3 minus 1. I don't think that's 2. Just do the rule. Bring the negative 3 out in front. And you can write this in slew steps. Bring the negative 3 out in front. Now you got a negative out in front. X to the, what is negative 3 minus 1? That's it. How are things going here, friend? Good. Great. Yeah. Nice. Outstanding. How you doing? Yeah? Okay, cool. This is where calc gets soothing. How's it going? Ooh, whoa, you got fancy. Hold on, let me see. Yeah, that's gorgeous. Got no complaints. Look at Victor. Good. That's looking good. That's good first move. All right, let's check out this. So what happened to your negative 2 that was up front? That was a good move. So if you have 1 over x squared, there should be a negative 2 up front. So that should still be there. That should be negative 2 x to the negative No, you just lost a little bit. X to the negative. Yeah, so there's negative 2 on top. Or no, because that would, no, negative 2, just write a number out front, so it's negative 2 times 1 over x cubed. So negative 2 would go on top. Yes. Yes, that makes sense? Yes. Oh, you're getting fancy. Yeah, you're feeling so good that you're getting fancy with it. That's awesome. That is exciting. Beautiful. Nice. How are you doing, Charlie? Yeah. Yeah. Wait a second here. Where did? Okay, so you know this interpreting the cube root. That should just be x to the root. Yeah. So yeah, let me address that up front because you're not the only one making that error. Friends, when you got a root, let's talk about that real quick. So if you have, there's an n in here of something, that's x to the 1 over n. If you have nth root of x to a power, you can do that a couple of ways, but probably just going straight to x. So first off, the 1 over n for the root, and then the nth power, like that. So these are things that you want to get good at translating. If I have 1 over nth root of x, that is 1 over x to the 1 over n, and that is x to the negative 1 over n. So these little subtle things, you gotta nail down, and today's a good day to do that. So coming through here, first rewrite it, then do it. Bring the negative 3 up front, exponent goes to negative 4. Rewrite it. Bring the 1/3 up front, decrease. 1/3 minus 1 is negative 2/3. Then you can get fancy and write that. So notice the 1/3 is still there, and then this is x to the 2/3 if you want. This is great. So like if you got to here, that's beautiful. You don't have to do all the rest of this stuff right away. At some point you want to be proficient at doing what I'm doing here. That's cube root of x squared. But these are all good, valid answers. And then this last one, convert to a power, that's x to the negative 1/3. Bring the 1/3, negative 1/3 out front. Decrease by 1, that's negative 4/3. You get really good with fractions in doing this stuff. And then if I wanted to, watch this, this is cube root of x to the 4th. And so if I put them all together, I could do something like this, which I've seen a number of folks doing. Just playing math games, making things pretty. Not any more correct, just in a slightly different notation. Questions on any of this? Claire, question?
No, I figured it out.
Okay, cool. You had the question hand up to your mouth, but okay. All right. Let's get some more stuff going on. So here's some basic rules. Basic derivative rules. This will let us do fancier things. Good. Derivative rules. So first one is that the derivative of the sum of two things. So I know how to do the derivative of this piece. I know this piece, but there's a plus. And let's put a plus or minus in there because this can go either way. And then this pairs up. So I've got something and something else, and they're connected with a sum or a difference. But I can do each one. And so I do that and just keep the plus or minus in there. Let me give you an example right away. What is the derivative of x plus x squared? It's going to be the derivative of x plus the derivative of of x squared. You'll get really fast at doing those. Let me stop. Tell me if that sounds okay to you. Okay, cool. And make sure to keep the plus with plus, and if it's a minus, it stays with minus. If I have the derivative of some constant times a function, and I know how to do the derivative of this, but there's like a 7 out in front, no worries. Bring that, keep that number along and just do the derivative, and then it becomes multiplication. So for example, the derivative of, I'll go 7, 7x squared. Leave the 7. Derivative of x squared is 2x to the first. I'm suppressing that first, but it's there. So 14x is that derivative. Stop. Those are the basics. Once we get to products and quotients, we got special tools for those. Things get a little more complicated. That's like Monday, probably. Any questions on that at all? Good. Okay. One on that power rule. I have this. You might want to go back. I just realized I had this. This is good as long as. No, never mind. Forget it. Everything's fine. You don't worry about it. I thought I made a mistake. Not made a mistake, but left out some important caveat. All right, so this is literally going to be a problem on the next exam. Let's see if we can do it today. It'll have slightly different numbers. Let's do some web workish practice. Can you please find the derivative of x to the 5th plus x 5th root of x? I get tricky and make you write it again. Plus 3 over x to the 5th plus minus 2 over the 5th root of x. There we go. If you can do this, you're ready for at least one problem on the next exam. I swear it'll be on there. So your step 1 should be convert everything to x to a power in those last 2 terms. I didn't stop up here last time. How's everything going, friends? How you doing? Is this making sense? Is that all right? Okay, cool. Mariana, good to have you back. Sure, it's good to be back too. Is everything making sense?
Yeah.
Okay. Diego, how are you doing? Decent. Okay, decent. I'll take that. That's all right. Pretty good. Any consultations needed? Okay. What's that little for?
That's not.
Oh, that's not supposed to be there. I like it better now. It's better. And so let me help you. So once you've actually done the derivative, get rid of it.
Okay.
Because that's a reminder to say derivative needs to be applied.
Okay.
And it
Let's just do it like, we drag that down all the way, so it's just.
Yeah, but once we did it, we got rid of it. So like use that notation to help your mind just.
Structure.
It's structure, yeah. It's like accounting. Like, okay, this is done. This
And
is
I did
column.
I haven't done the middle ones, but that is that.
That's yep, it's gonna be 2 times x to the negative 1 with a negative, but yeah.
Yeah, so with the negative.
Yes, sir. Yep. Keep on cruising.
We'll see.
Nice rewrite. Smoking. So I'm going to convert this to x to the 5th instead of going, because I'm not sure. I think you're misinterpreting what that means. That's the 5th root of x. You've changed it to whole root 5 squared root of x. That's a totally different beast. So this is x to the 1/5. This will be 2 over x to the 1/5. Does that make sense? Yes. Yeah, otherwise you're not gonna get to where you wanna go. That is looking good, that's looking good.
Kitcher, you feeling all right?
Oh, yes you are. That looks good. Yep, yeah, alrighty indeed. You know what time it is? I'm just kidding. Yeah, yeah, are you good? Okay, cool. Ooh, yeah, 6/5. This looks lovely. Ooh, except for one thing. Almost one. Oh, wait. What is 1/5 minus 1? Is it negative 1/5? So I would write it out, just like write out 1/5 minus 1. How would you actually compute that? Good, good, good. Like I said, gonna get real good at fractions. That should be your first rewrite. I think everybody was headed down the right road on that for the most part. There's definitely a few spots of confusion in the class about these roots. It's not isolated, it is spread out all over, so make sure you got that about the fractional exponents. So it seems to be, it's not just you. There's lots of folks who are having trouble with that. So then I go through and now, and here's something else I was telling Alex. This symbol means derivative still has to be applied. I haven't done the derivative. If I see this, you're using it to tell your brain, haven't done the derivative yet. It hasn't consumed these things and transformed them yet. So use this notation to help you keep sane. This is why mathematicians write stuff, because it leverages this for a part of your brain. So now I just go through. This is going to be 5x to the 4th. This is going to be, I bring that 1/5 up front, decrement. 1/5 minus 1 is 1/5 minus 5/5. And that is negative 4/5, my friends. And then I've got this 3, so I bring the 3 along if I want, and bring the negative 5 out in front. Decrement by 1. Got that's going to turn into a negative 15 on my next round. And then here I've got minus 2, bring the negative 1/5 out in front. X to the 1/5, negative 1/5 minus 1 is negative 1/5 minus 5/5. That is negative 6/5. And right now, that's like full credit unless the instructions say simplify completely. And it will. So let's simplify completely. So this is 5x to the 4th. I consider this simplified. But if we were going to write it in a pretty way to baffle our foes and friends for some reason, we're trying to baffle them with calculus, I don't know why.
The 5x to the left,
That is 5.
on the left side.
Yeah. Yeah.
Stop.
Yeah. 4.
There we go.
There we go, indeed. So then minus 15 over x to the 6th, and then plus 2 over 5 x to the 6/5, which, shit, I guess I'm being consistent, it's the 5th root of x to the 6th. I'm going to recommend don't go back to these root forms. They're not going to help you. In the end, we're going to be like doing equation work, and having exponents is the way to go. So like the optimal answer here would be 5x to the 4th plus 1 over 5 x to the 4/5 minus 15 over x to the 6th plus 2 over 5 x to the 6/5. In other words, just getting rid of all the radical stuff. It looks cool, but it doesn't get you any, it doesn't do anything good for you. Questions? Feel okay about this? We can do this. We're ready for the next exam already, at least about 10% of it. Okay, more formulas are coming. Every day for a while, I'm going to come in and we're going to talk about some new formulas. Today's kind of, I'm dumping a bunch of them on you. These I won't prove. The proofs are, we could do the proofs. Anybody wants to see them, I'll get together with you and give you the proofs. But they don't really provide any illumination, so. All right, check this out. Totally different than what we've had so far. And we really haven't done much with this at all. This is a constant, so A is a positive constant. Notice that my variable is the exponent. This is totally different than the power rule. This is not the power rule. Here we have a variable, and this is how you're going to key off to know this is the rule. Variable exponent. That's the trick. So you get used to looking for these patterns and then knowing what rule to apply. Here, this is equal to the natural log of A times A to the x. So the problem almost stays the same. It grows a natural log out in front. But it looks the same otherwise. So for example, the derivative of 2 to the x is natural log of 2 times 2 to the x. That's so easy, it's lovely. But there's one thing that's easier. It's the easiest thing in all of calculus is about to happen right now at 11:42 on this lovely Friday. The easiest rule in all of calculus is a special case of this. And it's going to become your dear friend. The derivative of e to the x. So again, e is Euler's number. On and on and on. We talked about that very first day, I think. Something like that. That sounds about right. I can't imagine who else I would have talked to about that this semester. You're my e friends. So this, according to that rule, would be natural log of e times e to the x. But what's the natural log of e? What's the natural log of e? Help me out.
Somebody Google it.
What's that?
I said somebody Google it.
Somebody, geez.
It's 1.
You know, it's 0 or 1, that's for sure. But it's 1. Yes. Yes. Oh, thank you. Almost lost it there. Natural log of e is 1, so that's just e to the x. Natural log of 1 is 0. That's a good thing to know. Natural log of e is 1. So this is just this rule right here, and I'm going to write it out in all its glory, that the derivative of e to the x is e to the x. You can't go right, you copy it down again. It doesn't change. It is invariant under differentiation. Very strange, but also very special. This is like a moment of great solemnity to see that. This is, E holds a special place in calculus, and this is just showing some of that. There's more. So let's see. What else do I want to tell you? Yeah, let's do another one. So your turn. Please find the derivative of 7 3 to the x. That's 7 times 3 to the x minus 2 e to the x plus 5. Let's find that derivative. Two more rules for today. Nope. Yep. Yep. How'd you get that?
So I was doing this, bringing it down, so it's.
Oh my, this is 3 over x, so I'm not sure what you're thinking. You're misinterpreting what this means. This isn't 3 to the power of x.
Okay.
So, like, according to your rule, like, if I was, so like 3 squared, just means 3 times 3. So that's just, but, so it's clearly not 3 over 2.
Yeah.
Right? So you're misinterpreting what that means. And so here, look, check out what I got. The exponent is a variable. That means I've got to use that top rule.
Oh, that's what.
Yes, yeah. When your variable is an exponent, don't power rule. Common mistake, super common mistake. Sometimes things look ugly and you just write them out. Derivative of that first piece is pretty much the same thing, but a natural log of 3 shows up out front. Here's what it's not. The derivative of 3 to the x, you're gonna maybe do this at some point. That's a lie. Don't even write that down so that you think it's some kind of legitimate thing when you look back in your notes. Exponent is variable. You've got to use that top formula over there. -2, best derivative in the world. Same thing, nothing changes. Derivative of a constant is 0. And you could leave this like this. If you wanted to get fancy, I'd just like to show this for the folks who like fanciness. You could bring this in as an exponent on the log, so it's 3 to the 7. 3 to the x minus 2e to the x. You could certainly drop the 0. This is just using log properties, that if you have a constant times the log of something, you can bring that constant up as an exponent, and vice versa. That's why people have logs, so they can make things that are powers multiplication. And then the old sailors of yore would have tables of these things to figure them out. Any questions on that, friends? Good. Fernando, you good, or you got a question? Yeah, good. Okay, awesome. Last formula for today. And we already kind of proved this with the graphs back in the day, and maybe this will ring a bell, but the derivative of sine is cosine. And the derivative of cosine, here's the one that tricks everybody up. The derivative of cosine is negative sine. So notice the change in sign there. When I differentiate sine, it goes to cosine. When I differentiate cosine, it goes to negative sine. There's kind of a neat thing here. Let me show you while we're at it. So if we had f of x is sine of x, f prime is cosine of x, f double prime of x, that's the derivative of cosine now. So I'm just taking, each time here, I'm taking the derivative. Derivative of cosine is negative sine. F triple prime of x. You'll bring the negative along. What's the derivative of sine? It's cosine. So it's just negative cosine of x. And then fourth derivative of x. It's negative times the derivative of cosine, which is negative sine, so I'm back to positive sine again. And then these repeat over and over. They cycle back over and over again. So we're kind of cool that these periodic functions that already are periodic within themselves, when you look at the graph, they're periodic here as well. The derivatives repeat and cycle forever and ever and ever. So that's, is there a connection there? maybe. So let's do one last problem. Find, oh, you're gonna like this. Find the equation of the tangent line to y equals x plus sine of x at x equals pi. Let's do it. Let's try it. So let's go through our routine, right? We've got a routine for tangent lines. There's going to be a couple of these in the web work. Step one, get our point. Well, I've got the x coordinate, and this. Let me show you what this graph looks like. It's kind of like a sign that goes up like that. If you were to sketch it out in Desmos or something, that's roughly the graph. So step one, get the point. When x equals pi, that was given, right? Y equals pi plus the sine of pi. And what's the sine of pi?
Zero.
Zero. It's 0 or 1. Hella good guesses. Sine of pi is zip. All right, here's my sine graph. 0. So this is pi plus 0, good old pi. So my point, x naught, y naught, is pi. That's cool. So, something like this, where I kind of think it's going to be like that. But we'll find out in a minute. That point might not be where it's at on the graph. I'm not totally just guessing. In fact, it probably isn't, but that's all right. Any questions on what I've just done? Let me know, because sometimes the trait can get a little, I know, heady or confusing. All right, so I got my point. Step 2, get the slope. And that's going to be the derivative at my point of interest. So here, m is going to equal, well, I need the derivative actually here, so we better find that first. So here, f of x is x plus sine of x. F prime, what is f prime going to be? You find that, please. While I clean up the board. Anybody care to regale us with that? Yes, Kelly.
1 plus cosine of x.
Beautiful. 1 plus cos. Thank you. Derivative of x is 1. Derivative of sine is cosine. And then we just add the results. That's cool. So now we need to find the slope. So m is going to equal f prime at pi. And that's going to be 1 plus cosine of pi. It looks like I did a pretty damn good job of guessing roughly where that point was, because that's 1 plus what's cosine of pi?
-1.
Oh man, you are on fire today. So yeah, -1 cosine of pi, right? So that's 0. So it's actually flat, and it is one of these peaks or these troughs where this line is occurring, because that's where our tangent's 0. So m equals 0. Huzzah! Step 3, use point slope form. which says y equals m times x minus x naught plus y naught. Plug in the gunk. So y equals 0 times x minus pi. We'll pretend like this matters for a minute. And then our y naught was pi. So check it out, y equals pi. It's just a constant. It's a constant line. Because it's at some kind of peak or something like that. That's a lot. It's a lot of calculus in one day. You've paid dearly to have things become this clean. So friends, that's it. Let's call it a day. It's been an intense week for you especially. Me doing exams. And I would love to answer questions on the web work on Monday. That would be outstanding.
What's that do again?
What's that?
What's that do again?
Wednesday. We got lots of time. And remember, if grades go in the book, you're going to get a chance to get more points. So don't get stressed about that exam at all.
Thank you.
Thank you.
Before we did all that.
Oh, okay.
We didn't need to do all that.
What do you mean? Yeah,
The derivative.
thank you. Well, that's the derivative, but
Which gave us the slope, right?
right. Yeah, but you still need to go to the point. You're lucking out that it turned out. You still need to go. You still have to go to this. With nothing else. But good work. Thank you.
Really quick question.
Yes, sir.
And then,
But I have like equation that has divided.
Much easier to write.
So I have like x,
I don't know.
y,
Oh, okay.
equals c.
Yeah.
So this is actually x times c times y. Yes, sir. So my question is, if in this case the y is negative, it will pass here as negative. Correct. So over here, the whole equation will be x minus y, or it will be just x minus this divided by minus y.
Those are equivalent. So they're saying that
It's the same.
yeah. So this is equal to this is equal to this. As well.
Okay, and in that case, if I want to, I don't know, simplify y, doesn't matter if I leave or I take the negative.
That's right.
It's just, it doesn't matter.
Doesn't matter. As long as the negative doesn't just magically disappear somewhere in your computation,
Okay.
you're going to be okay no matter where it shows up.
Okay, awesome.
Oh yeah. Okay. Awesome.
Thank you, yeah.
That's good. Is this for some other class one?
No, it was because sometimes I just get like in the middle of the exam, I'm just like, oh, I don't know how to.
Yeah, I don't think you're alone.